Let's look at how to do a significance test for a population mean. These are actually data we've used before. So in our high school's U.S. News and World Report rankings, we are listed as having a 20-to-1 student-to-teacher ratio. So we're going to use that as a representation of class size, if you will. So is there evidence that the real average class size, so notice this is not about a proportion anymore, this is about a mean. So the real average class size at Westfield High School, we're going to call that mu. Means are represented with the lowercase Greek letter mu. Do we have evidence that the real average class size is greater? So I've gone ahead and I've entered all 17 of these class sizes into the graphing calculator. You are welcome to do that if you want to, although technically you don't have to, because I've already given you screenshots of what will happen on the graphing calculator. You'll want to use your graphing calculator in order to complete the test here in just a second, though. So let's actually go back and look at those class sizes. So I'm just going to pull up my calculator here. So I'm going to run one variable statistics on my data. So my data are in list 1. So this is exactly the same screen that you can see on your handout. So the average class size in our sample is about 24. The standard deviation is about 5.6. There are 17 observations. And then notice on the handout, I gave you window settings. So something else that I would want you to be able to do, this is the X minimum, the X maximum, and the X scale. Here's the Y minimum, the Y maximum, and the Y scale. So certainly by this point in the class, you would want to be able to set up this window and be able to use your stat plots in order to plot a histogram of the data. Here is a histogram of the data, which will actually be important to us in just a second. Here's what the graph looks like, same thing. Don't forget, when you do a histogram, when you graph a histogram, if you press trace, you can actually press the right and left arrow, and it will tell you the number of observations that you have in each bar of your histogram. So bottom line then, I am interested then in doing a test regarding mean, the real average class size. This is the sample average. This is the sample statistic. So U.S. News and World Report has reported a 20-to-1 student-to-teacher ratio, so we're going to act like that's our average class size of 20. And that will give us our null hypothesis value. So the null hypothesis, if nothing special is true, the average class size, so I'll call it mu class, is 20. So, but notice up here, we're looking for evidence that the real average class size is greater. So greater is what gives us the direction for our alternative hypothesis. I'm looking for evidence that the real class size is greater than 20. So the conditions are just like we did before with confidence intervals. So for randomness, this is a random sample. So you should say that. The sample of 17 classes is random. So for independence, you should check the 10% rule. So 10 times 17 is 170, and that's certainly less than or equal to the number of classes at WHS. So now, remember, the normality condition for means does not involve successes or failures. We checked n times p and n times 1 minus p, the success and failure counts, when we were working with categorical data, when we were working with proportions. Well, here we don't have success and failure. Means involve quantitative data. The normality condition here regards having a sample size that's large. When the sample size is 30 or more, that's our boundary for large, 30 or more, the central limit theorem is what allows us to conclude that the sampling distribution for the sample means will be approximately normally distributed. Well, notice our sample size is less than 30. So we can't just say, hey, we've got a large sample, so normality is met. So a smaller sample can still be acceptable, like we talked about with confidence intervals, as long as you don't have any serious skewness and you don't have outliers. We'll take a look at the graph. This is why you needed a graph of the histogram. I don't see any skewness in that graph. And what's nice about your graphing calculator is you could very quickly check for outliers if you wanted to, just by going into your stat plot and switching from a histogram to a box and whisker plot. So there you go. In the box and whisker plot, I don't see any outliers indicated there. So for normality, the sample is less than 30. The sample size is less than 30. But there are no outliers. Nor, I'll just call it serious skewness. Actually, and from the histogram, I really don't see any skewness at all. So randomness and independence and normality are met. So remember, when we studied confidence intervals, remember our critical values were not z-scores, our critical values were t-scores. The same thing happens when we work with significance tests. So these are the things that you want to list when you complete a test for a mean. So the test name, this is a one sample t-test. Again, means use t's. So for the test statistic, I want to write down my t-score instead of z-score. The test statistic requires degrees of freedom. We'll talk about that in a second. And then your p-value. So I need a t-score. I need my degrees of freedom, and then I need my p-value. Well, remember, the degrees of freedom here is just one less than the size of the sample. Remember, we're going to use the sample standard deviation instead of the population standard deviation. And for the sample standard deviation, its degrees of freedom are n-1, and its calculation, we divide by n-1. So our sample size is 17, so the degrees of freedom, 17 minus 1. So the degrees of freedom are 16. So that's supposed to be a 17 minus a 1 instead of what looks like 17.1, forgive me. So for the t-score and the p-value, let's let the calculator do the work for us. So if you press the stat button, and if you go over to tests, here is the t-test. There is the t-test. This is a one sample t-test. So something I want you to notice, INPT stands for input. So if the data are in your calculator, you can literally tell the calculator what list the data are in. So if I wanted to do this test, one of the things that I could do, and if you've entered the data into your calculator, you can do this. So let me specify my null hypothesis value. If you remember, the null hypothesis value, that's the 20. So my data are stored in list 1, so I could press second 1 for list 1. Don't change the frequency, leave that as a 1. So notice then we have to specify the direction of the alternative hypothesis. So we've already written our alternative hypothesis. It's a greater than alternative, so I need to select greater than. So if we wanted to, then we could highlight calculate and press enter, and we will get our t-score and our p-value. So in the event that you didn't enter the data into your calculator, that's fine. The other thing that you can do instead, and this is what I would expect most of you to do, is to select the stats option here. So if I highlight the stats option and press enter, notice I don't specify a list anymore. Now what I'm going to do is specify the mean and the standard deviation that I want to use in my test. So the null hypothesis value is still the 20. Notice the calculator has just filled in the mean and the standard deviation that I had in list 1. You don't need to keep all of those decimal places. So I'm going to call the mean 24.1. I'm going to write over the standard deviation. I will call that 5.6. You still have to tell it now the sample size, which is 17. It's still a greater than alternative. And now if you highlight calculate and press enter, it will give you the t-score and it will give you the p-value. There's the sample mean that we input and the sample standard deviation and the sample size. So I'm going to write down my t-score. It's 3.019. So, and my p-value is 0.004. So that's where those come from. So I wrote down my t-score. The degrees of freedom are 1 less than the sample size. And the p-value was 0.004. So the t-score is the test statistic. Proportions, like we've done previously, involve z-scores. Means will involve t-scores. But the nice part is writing the conclusion is just like we've done before. So I'm giving you an alpha level of 5%. So you should compare your p-value to that level of significance to alpha. That's less than 5%. So because of that, we can reject the null hypothesis. So rejecting the null hypothesis, we call that the decision. So when your p-value is low, you reject HO, you reject the null hypothesis. In other words, this is an unlikely outcome, so we do reject the null hypothesis, so we do have evidence of the alternative hypothesis. And so you can just use the words in the question. So we do have evidence that the real average class size is greater than 20 students. We can just use the words in the question. You can do that on the AP exam or on a unit quiz or test, doesn't make a difference. So we do have evidence. That, and so I'm just going to copy the words. The real average class size So I'm going to include a little bit more at our school, at WHS, a little more context there, is greater than 20. And that's the end. So 4 things, just like with a test of significance for proportions, tests for means, same thing. Number 1, you have to write your null and alternative hypothesis. So instead of using P for proportion, we should use mu for means. You need to, number 2, check your conditions. The conditions are for randomness, independence, and normality, and the condition that's different is the normality condition. So number 3, you have to give your statistics or show your work. So you should write down the name of the test, means or t-tests, and we're only using 1 sample worth of data. So this is 1 sample t-test. Give your t-score, the degrees of freedom, and the p-value. And then last, write your conclusion. And we write our test conclusion just like we did for proportions. You compare to alpha. So if you do have an unlikely result, then we do reject the null hypothesis, and we do have evidence of the alternative. If the p-value is greater than 5%, we don't have an unlikely result, so we don't reject the null hypothesis, and we don't have evidence of the alternative. So let's finish up this example on the last side. So let's think about error types again. Which type of error is possible here? Well, remember, for a type 1 error, that's when we reject, but we shouldn't. A type 2 error is that we don't reject when we should. Well, notice we did reject. So the only type of error that's possible is a type 1 error. The type 1 error occurs when we've rejected the null hypothesis, which has happened here, but maybe we shouldn't have. So what type of error is possible? This is a type 1 error. So describe the above error in context. So we don't know if we have made a type 1 error or not. But if we have made a type 1 error, let's describe what this means about what we believe. So remember, a type 1 error means that we have rejected the null hypothesis. So we believe that we have evidence of the alternative hypothesis. So the above error means that we believe the average class size may be greater than 20. So if you reject the null hypothesis, then you have evidence of the alternative. So this is the alternative. We've rejected the null hypothesis. So we believe the average class size may be greater than 20. But if it's an error, we're wrong. So the real class size is actually 20 or less. So describe this error. We believe the average class size may be greater than 20. But what's the truth? The truth is we're wrong. But the real average is 20 or less. So to describe an error in context, you compare what you believe to what the truth really is. So what we believe is we have evidence of the alternative. We believe the average class size may be greater than 20. But if we've made an error, the truth then has to be that the real average class size isn't greater than 20. It's 20 or less. So now there's a difference between describing the error and describing what a consequence of that error might be. So wait a second, if we believe the average class size really is larger than 20, so wait a second, if we think class sizes are getting a little bit on the larger side, what might we do? Well, maybe we will hire more teachers in order to create more classes and make smaller class sizes. But wait a minute, we're wrong. The real class size isn't really that big. It's not greater than 20. It's 20 or less. So the consequence is we're spending money to hire new teachers where we don't really need them to lower the class size. So maybe that money would be better spent elsewhere. So we might spend money. We might spend money to hire teachers. To create more classes and lower their size. Oops. So wait a second, if we think class sizes are on the bigger side, we might spend money to hire teachers to create more classes and lower the size. But we didn't have a class size problem, so we're spending money when we didn't need to. We should be spending it in a different way. We might spend money to hire teachers to create more classes and lower their size, the size of those classes. But there was no reason to think that we had larger class sizes. Class sizes weren't that large. So maybe we could have better spent the money elsewhere. So remember, when we do a significance test, if you reject the null hypothesis and say you have evidence of the alternative, that doesn't necessarily mean you're right. You might be right. But it's important to think about what the consequences might be if you've made an error. So this is a type 1 error. And if you are worried about the consequence of a type 1 error, if you want to make type 1 errors less likely, well, then you can lower your level of alpha. Type 1 errors probability is controlled by alpha. So if you're worried about making a type 1 error, then lower your level of alpha to 1%. So, and at 1%, we would still reject the null hypothesis. So the point is, don't forget that just because you perform a significance test doesn't mean you were right. That's why, at the very least, we need to be able to identify the different types of error, what they mean in context, and what the consequences of making those errors might be.